Okay, thank you very much. So perhaps an apology to begin with. I don't really feel like I'm an expert in transcendental dynamics. I don't know a great deal of what's going on. I have thought about a few particular problems. And so I think I have to restrict myself to the small parts of transcendental dynamics that I've thought about. So it's going to be a little bit of a narrower talk than Anna's terrific talk this morning. Also, those of you who have heard me speak before on this topic will have seen lots of these slides and a lot of this material before. So it's intended to be maybe an introduction for people who haven't seen so much of this. I'm worried, though, that it'll be too boring for the experts and too quick for the non-experts, but we'll try to go in the middle somewhere. So mostly what I wanted to talk about are these things, the Speiser class and the Eremenko-Lubitsch class, which Anna had introduced in her lecture this morning. To state a few theorems carefully, we're going to have to talk a little bit about quasi-conformal mappings. And so I'll spend a couple of slides on that. And then there are two theorems I want to describe. One is sort of gives the structure of what Eremenko-Lubitsch class functions look like. And the second is something Anna referred to, quasi-conformal folding, which is sort of what the Speiser class functions look like. They're a little more specialized. And so they have a little extra structure. So I just try to describe that. And then there's a long list of possible applications that once you understand what these classes of functions look like, that you can try to prove various things or do various things with them. And I'm going to talk about two of these possible applications. One is specifying the singular orbits. Now, the singular points and the singular orbits are very important in dynamics, and it's reasonable to ask, well, what can they possibly be? And the answer is pretty much anything that you want. And so we'll talk about that. And then the second thing I'd like to talk about is some work with Laszlo Rempe on equilateral triangulations of surfaces. That comes in, doesn't sound so dynamical, but basically the proof is closely related to building Speiser class functions. And it does give rise to a lot of new finite type dynamical systems. And so it sort of introduces a new branch of holomorphic dynamics, which I hope will be of interest in the future. So let me just repeat what Anna said before. The singular set, I take it to be a closed set. It's the closure of the set of critical values and the finite asymptotic values. Those are the finite asymptotic means that you have some curve going off to infinity, and the function has a limit along those. Those are not going to be so critical to us today because most of the examples we construct are going to have critical values, but either will not have asymptotic values or will only have a very few of them, and try to point them out when they occur. The two main things we're interested in are the Eremenko-Lubitsch class, which has a bounded singular set, so all the singular values lie in some disk. Usually for convenience, we'll think of that as the unit disk. But you can always take an Eremenko-Lubitsch function, multiply it by a constant. So if they're all trapped within the radius 10, and you divide by 10, then they're all trapped within a disk radius 1. So usually we just take the bounded singular set to be inside the closed unit disk. And the Speiser class is a finite singular set. And again, for simplicity, it's very common that we just restrict to the case when there are 2 or 3 singular values. So a rather small number. Okay, questions so far? Okay. Well, the point about an Eremenko-Lubitsch function is that when the singular sets are in this small set, so again, I'm assuming here that they're in the unit disk, as I said before, that if you look at the places where the function is bigger than 1, there are no singular values there. And so what one can show is that the components of where f is bigger than 1 are simply connected components, and we call these tracks. And so the tracks here are these dark green things. These are the places where f is bigger than 1 in absolute value. What's left over, so the thing which is, well, let me choose the white region, which now I'm shading green to make it look like the green region, which is maybe silly. The region between that's where f is less than 1. So f is less than 1 on this white region. And that's where, if they're going to be critical points, all the critical points are scattered around. in this region. Okay, now what does the map look like? So this is the place where it's bigger than 1 and the place that it's less than 1. On the place that it's bigger than 1, those tracks we can think of, they map to the outside the unit disk, but it's convenient to think about them first mapping to the right half plane. So first going over here and then going down to the outside the circle, because the first map is conformal. So just a one-to-one holomorphic map of each track into the right half plane, and then followed by the exponential map. And so we understand conformal maps pretty well. There's a whole literature from geometric function theory about understanding conformal maps to a half plane. And the exponential function, well, we already understand that very well as well. That's a very explicit function. What's mysterious about these functions is that the white part maps into the unit disk. And that's where all the complication is. And so in some sense, if you have an Eremenko-Lubitsch function, where the function is larger than 1, we have a very good picture of what that looks like. And where it's less than 1, the place where the singular values can occur, that can be quite complicated. And that is what is sort of different about each individual function. Okay. Now, one additional thing that you can do is on the half plane, it's very natural to put dots, say at a distant unit evenly spaced. Usually the distances here we think of as being 2 pi. So that these all map to a single point on the unit disk. And then you can look at their pre-images. And your pre-images will be an infinite number of dots on each of the tracks. This introduces some geometry. So this is sort of telling us there's a natural scale that, this is sort of the natural unit distance on the boundary of these tracks. It corresponds to basically a unit distance in the half plane. And part of what I want to express to you today is that in the Eremenko-Lubitsch class, these dots are not so important. That's really just the shape, the topology of the tracks, which is important. For the Speiser class, when we only have a finite number of singular values, then the distribution of these points, how the boundaries map over, what are the unit sizes on the boundary, those become more important. So the Speiser class involves some geometry, whereas the Eremenko-Lubitsch class is primarily just a topological thing. Okay, so here's our picture of Eremenko-Lubitsch functions again. So we have the tracks mapping conformally to the outside, and then we have the white region that maps to the disk. Now, the tracks are connected, so the white region that separates them is simply connected, so you can actually map it. There's a map of the disk to that white region by the Riemann mapping theorem. And then F maps it to the disk again. And so when you put these things together, what you get is a mapping of the disk into the disk, but it can be many to one. And this is what we call an inner function. So in particular, the boundary points here go to boundary points on the track. They go to boundary points on the disk. And so, in fact, the region between the different tracks is naturally associated to an inner function of the disk to the disk. And this inner function is basically responsible for all the critical values of the function. Okay, a common example of an inner function, for example, is a Blaschke product, something of this form. So if you study some complex analysis, you may have seen this. Okay. All right. So the question is, this is what an Eremenko-Lubitsch function looks like. If you're given a function, then you have this picture. You have conformal maps on the tracks, and you have the inner function on the interior, on the complement of the tracks. The question is, can you go backwards? Suppose I don't give you an Eremenko-Lubitsch function, but I give you this picture. So I give you this. Is there an Eremenko-Lubitsch function that goes along with this? So if I just give you the tracks and I give you these taus, is there a way to build an entire function that sort of fills in the gaps between the tracks? And the answer here is yes, but it'll take a little bit of work to get there. To make it a little bit more precise, a model, oops, I didn't mean to fix that. I just wanted to highlight. So a model is a set of tracks. Omega is a set of unbounded Jordan domains. So the omega is the thing that looks like this. There'll be a lot of these components, infinitely many of them. And then from each track, you have a mapping to the upper half plane. And I don't say anything about what goes on inside. I'm just giving you that on the tracks, we have these tracks, and then we have conformal maps to the half plane. And those, given the tracks, the conformal map is determined. If I'm going to map a track to a half plane, that is completely determined up to a factor of a lambda. So after I map the half plane to itself, I can shift it upwards, or I can multiply by a lambda, and that's all the freedom I get. So the track pretty much determines the conformal mapping. But does every model give an Ehrenmann-Lubitsch function? And I'll just cheat, and I'll tell you the answer is yes. But to state the theorem, I need to say something about quasi-conformal mappings. So, questions so far? We're doing okay? Can anybody hear me, or am I just talking to myself?
It's fantastic, and we hear you very well, and we already have a question.
Is there any
okay, what's the question? I'm not reading the chat, so
tracks?
Please just break in and ask me.
Is there any reason to think there are finitely many tracks?
There could be. The case when there's finitely many tracks is particularly interesting. If you have infinitely many tracks going out to infinity, then some of them have to be quite narrow. And if the track is quite narrow, that means that the function f has to grow to infinity very fast inside it. So a wide track, something that has like a big angle here, that can allow for a fairly slowly growing function. But a track which is narrow has to go to infinity super fast. So something that has an angle in it can grow sort of like e to the z to the alpha. It's what we call finite order. But a track which, say, for example, has angle 0 when viewed at infinity, it has to basically go like e to the z to the infinity, if that makes any sense. It has to go faster than any, it has to have what we call infinite order of growth. So all the examples of functions that have what we call finite order only have finitely many tracks. Well, that's at least philosophically true. I might be making a technical mistake, but that's the main idea. So many of the common examples of finite growth entire functions in this class, they will only have a finite number of tracks. But either case can happen. Does that address the question?
Yes. Yes, it was a yes.
Okay.
No, because the speakers don't hear if we don't speak in the microphone. So John Hubbard said yes, but well, please keep going.
Okay. Yeah, thank you. As I said, I'm not reading the chat, and I'm not lip reading any of the pictures that come over. So I'll depend on Anna or the questioner to just break in. So QC mappings are homeomorphisms of the plane to the plane. We can think of them as being differentiable. And technically, they're differentiable almost everywhere, but they send infinitesimal ellipses to circles. And the ratio of these ellipses is bounded. That's the critical thing. So you can't have arbitrarily thinner ellipses occurring here. You could easily teach a whole semester-long course on quasi-conformal mappings. I just sort of want to summarize the main things in a couple of slides. In terms of differential equations, you can take the z bar derivative over the z derivative. That ratio gives you mu, and this complex number encodes the ellipse field. Basically, the absolute value encodes the eccentricity. What's the ratio between the minor and major axes? And the argument of this number encodes the direction of the major axis. What direction does it point? And the fact that mu encodes this information, basically you just have to compute the linear approximation to f say you think of it as a function of two real variables, and you can work it out, and this is what it comes out to be. Now, the eccentricity being bounded corresponds to mu being less than 1, strictly less than 1. So k being less than infinity corresponds to this mu being less than 1. And so we have a dilatation which is associated to every quasi-conformal map. I tend to like to think of things discretely, and one of the most common examples of QC mappings is just if you take a triangulation, you can map each triangle affinely to an image triangle. So very often we'll have a domain and we'll cut it up into pieces like triangles and map it forward. And the new pieces are triangles, and the mapping is just distorting each triangle in an affine way. And that, what quasi-conformal means there is that the angles are basically being distorted by a bounded amount. That, assuming that you began with all, say, right 45-degree triangles, it would be quasi-conformal if and only if the angles in the image stay away from 0 and 180. And so it's really instead of preserving angles, it's a bounded angles distortion condition. For people who are a little bit more expert, if one takes two triangles and fixes them to have one common edge, say 0 to 1, then you can easily compute the affine map, which just takes the third vertex in each case to the other one. And in this case, mu turns out to be b minus a over b minus a bar, which is the pseudo-hyperbolic distance between these points in the upper half plane. So if you think of 0, 1 being on the real line, then when these points are very close to each other, you're not distorting the triangle very much at all. You have a very small quasi-conformal distortion. But if you want to map it to a triangle which looks very different, you need a lot of distortion. And it turns out it's just the sort of like the hyperbolic metric in the upper half plane, what we call the pseudo-hyperbolic metric. So this makes it very computable when you have an affine map between triangulations. So something like this, you can draw a picture and you can easily check that this is a quasi-conformal mapping. And if you're interested, you can check, well, this triangle goes over to here with 0 distortion. So mu is 0, and this one, nothing happens. And for example, this triangle goes over to this triangle, again, mu is 0. It's similar, you haven't distorted it. A triangle like this gets mapped to this, and then you can see, aha, this one has been distorted. So that has a non-zero dilatation there. Okay. Now, the amazing thing, the thing that's so useful, is that given the QC mapping, you get this dilatation, but you can go backwards. If you're given a dilatation, which has the bound that its supremum is strictly less than 1, then there is a quasi-conformal mapping that has that dilatation. Here I've written it as going to disk because I was thinking of the dilatation on the disk, but if it was defined on the plane, the same thing would be true. If you had a measurable function on the plane, whose L infinity norm is less than 1, then there's a QC mapping of it. And so we're going to make use of this. And in particular, we're going to use a corollary of it, which says, suppose that we have a holomorphic function. So the holomorphic function is here in the middle. Since it's holomorphic, it sends circles to circles, or it sends ellipses to ellipses of exactly the same eccentricity. The holomorphic map can just, turn them a little bit, but it doesn't change the eccentricity. I can follow that by a QC mapping, and the QC mapping distorts. So it can take an ellipse and make it into a circle. And when I compose these two things, I have ellipses going to circles now. And this is what we call a quasi-regular map. It would be quasi-conformal, except the holomorphic part could be multiple to 1. It could be 2 to 1 or infinite to 1. And QC maps are homeomorphisms. So basically, a QC mapping, which is not necessarily 1 to 1, is what we call quasi-regular. But if you just want to think of it as always being a holomorphic map followed by a quasi-conformal map, that would be fine. Okay? What the mapping theorem says is that, well, given this quasi-regular composition, you can compute its dilatation, mu, and then when you apply the mapping, you can choose H so that it exactly undoes the distortion. So H will send, so really, the mapping says you can find a mapping H inverse, which takes the ellipses and maps them all to circles. Well, if the inverse does that, then H takes circles to ellipses, F takes those ellipses to other ellipses, G takes those circles to circles. So the composition takes all circles, all infinitesimal circles to infinitesimal circles. So it's a holomorphic mapping. And this is what we call a straightening. So the basic idea is whenever you want to build a holomorphic function with certain properties that you like, you can usually try to just build a quasi-regular thing by hand. For example, you could triangulate a region and then map that over to some other triangles and say, aha, this mapping has the property I want, but it's not holomorphic. And then you have to pre-compose it with a QC mapping and get a holomorphic one. And with luck, pre-composing by H doesn't destroy the property that you were so interested in. And most of the talk is about how this works and making this work in different situations. Okay? So for the model theorem, what happens is, suppose that you give me any track. I've only drawn one here, but again, there could be a lot of these tracks going on, many, many of them. this track maps to a half plane. So the light blue is the track, it maps to the dark blue. We have to smooth the track off a little bit. So the way we smooth it off is by taking a vertical line at some rho bigger than 0 and taking its pre-image. And its pre-image is a nice analytic curve inside the track. Okay. And if we had some other tracks, we would smooth them off in the same way. Okay. By mapping to the disk and pulling back. And now what the model's theorem says is that we were going to try to build an Eremejka-Lubitsch class function by taking this conformal map in the track, and then we were asking, can we find an inner function on the rest of the plane which matches up with it on the boundary and defines an Eremejka-Lubitsch function? And if you're in the quasi-regular class, you can exactly do this. What the theorem says is that if you restrict yourself to this region, the smoothed off region, then you can find a quasi-regular function which is exactly equal to what you want. It's exactly equal to tau followed by the exponential function, taking you to the outside of the disk. So that part you can get exactly. And off omega, out here, the thing is less than e to the rho, which is about 1. So rho is going to be a small number, so e to the rho is just a little bit bigger than 1. And this is what we wanted. We have exactly the map we want, and the outside, everything outside the track is basically mapped into the unit disk. If we multiply by e to the minus rho, it'll map exactly into the disk. And the only place we don't really quite understand the function is in this little strip between where we smoothed off and the outside. On the outside, we know it's mapping into the disk. We're happy with that. On the inside, in this smoothed off track, we know exactly what the map is. It's exactly equal to something we know. We're happy with that. In between, it's continuously interpolating between these two behaviors. That's where we have to pay a little bit of attention. But this is basically good enough because we're given something which is quasi-regular, and now we could use the measurable real mapping theorem to correct this map to make it into a holomorphic map. Okay, so this is the picture of how one can create any Eremejka. Every Eremejka-Lubitsch class looks like this picture, and given this picture, there's an Eremejka-Lubitsch class which looks like it, except for this quasi-conformal correction you have to make. But if you're a topologist and not an analyst, and you don't care quite so much about the metric, but only the shape of things sort of in general at infinity, this completely describes what Eremejka-Lubitsch functions can look like, right? Questions like this about this? Here's some technical remarks. Maybe I won't go into these so much. Okay. How do we improve from a bounded singular set to a finite singular set? So this is a little neater version of the picture I just drew you. We have a bunch of colored tracks. These are the places the functions are bigger than 1. They map conformally to the right half plane, and they map to the outside of the disk. The regions between them, this is where the function is bounded. That's some kind of inner function. It has all kinds of critical points all over the place, and they can go to singular values, which are scattered everywhere in the disk. Okay. What you can think of is that we have these sort of rigid tracks. Once I draw the pictures of these tracks, the conformal map is more or less determined, and the exponential function is completely determined. So I don't have a lot of freedom on these tracks. The inner function is some kind of glue, which is sort of fills in the gaps between the different tracks. If you've ever done some woodworking, you might know that when you're doing moldings, you're attaching molding to a wall. You come to a corner of the wall, and you want to attach the molding here, you have to cut like a very careful 45 angle degree cut in the molding so that they fit together. And it looks seamless when you paint over it. If you're like me, you can never do that. The angles don't quite come out exactly to be 45, and there's always a gap between the two pieces. And you have to fill it with wood putty and sand it off and then paint it over. And the wood putty sort of hides the gap. And in this picture, that's what the inner function is doing. You have these rigid pieces, and the inner function is hiding the gap between them. But we have to throw that away when we go from allowing infinitely many to finitely many. Suppose that we just allow 2 critical values at plus and minus 1, and we draw a line segment between them. Then the pre-image of that line segment, all these 2 points have all these different pre-images under F, and the line segment goes to analytic arcs that connect them. Okay? And now what we're going to do, instead of taking the exponential map from the half plane to the outside the disk, we're going to take the Koch map. The Koch map, whoops, didn't mean to do that. The cosh is basically, you just take the outside of the disk and you compress it into the disk by the map z plus 1 over z all over to the Joukowski map. And what happens now is that now we have mappings from the outside of this tree to the right half plane, and they get mapped to the outside of the segment. And what we've done is gotten rid of the gap between the different tracks. So it's the same kind of picture, but now instead of having a nice white region between them, where we can put the wood putty or the glue, there's nothing. We want to attach each track to itself directly with nothing in between to sort of mediate. This is harder. Okay, so this is this requires that we can't use any putty. We actually have to cut everything precisely so they fit. And so this becomes a little bit harder to do. So again, what we're going to do is we're going to build a quasi-regular function g, which does exactly this, which basically, if we take a smoothing of this, if we sort of cut out a neighborhood of the boundary here, we're going to build a g, which is exactly the map we want. It's right on. And then when we have to fill in across the boundary here, then we're going to have to do that in a slightly different way, not using an inner function, but doing it in a slightly different way. So this requires a couple of assumptions on the tree. So I don't know how to do this in complete generality. And you can prove that you can't. You need some assumptions. Basically, you have to talk about a neighborhood of the tree. I have to talk about the edges not being too close to each other. And I have to show that the lengths of these edges are well behaved. So let me just try to go through this relatively quickly. Given an edge of a tree, we just take a neighborhood of it, which is everything which is within a constant times its diameter. So a big edge has a big neighborhood and a small edge has a small neighborhood. This is sort of a Hausdorff distance. When we do this for each edge of a tree, what we get is a sort of a Hausdorff neighborhood of a tree, but which is adapted. The neighborhood is thinner around small edges and it's bigger around big edges. If needed, you can always add extra vertices to the tree. And when you add extra vertices, the edges get shorter and these neighborhoods will get thinner. So that's something we often do in our applications. The main condition, though, is that the edges should be pretty smooth curves. So we want everything to be basically at least a C2 curve. Usually it's analytic. Often it's a straight line or a circular arc. We only want a bounded number of these arcs to come together at one point. When they do come together, they have to form a pretty nice star. They have to be a bi-Lipschitz image of just a radial star. And edges that don't hit each other cannot come very close to each other. So if you know some things about extremal length or conformal modulus, if you have two edges which are not touching, then the path family that sort of separates them has a modulus estimate. So you don't have our two edges that look like this, that they come very close together without touching. We don't allow that. But if you have an infinite tree in the plane that has this bounded geometry, then we're happy. The other condition is that when you map one of these infinite connected components to the right half plane, remember these dots? Well, before I was taking unit dots on the plane and mapping them back. Now what I'm doing is I'm taking dots, the vertices of the tree, and mapping them forward. And what I want to say is that they are kind of evenly spaced. What I want at least is that the distance between them is at least pi. Now they can separate, they can be much further apart. I can take spaces like e to the n, so they get much wider apart. That's fine. Well, absolute value of that. So I want them to be spaced apart. This is kind of a global condition. If you have a track which has angles, say, greater than pi, then the mapping to the half plane is a power less than 1. And so evenly spaced points here, for example, become much closer on the half plane, and that's bad. So roughly speaking, this condition is saying that each of the tracks is not thicker than a half plane at infinity. It's thinner than a half plane. And I won't go into that too much, but that's sort of the general idea. And then the folding theorem says, if you have these two conditions, if you have the bounded geometry and you have the tau lower bound, these two technical conditions, then there's a quasi-regular G, just as advertised. It exactly equals the cosh tau. So on the light blue portion, you exactly conformally map over, then you apply the cosh function. Basically, that looks like the exponential, but it goes onto the line segment instead of the circle. And you have uniform bounds on everything. So as long as you had whatever the bounds on the bounded geometry you have, that's all you need. And you get a quasi-regular mapping. To get a holomorphic one, you have to use the measurable Riemann mapping theorem and fix this up. Okay, but then, so that's how it works. You build a quasi-regular mapping like this by hand. The folding theorem says that what you can specify is for the map out here exactly, and there's some way of filling in across the tree to make it quasi-regular. That's where the magic happens, is filling in across the boundary here. I won't say too much about that. Maybe I'll just give one very brief hint about why the name folding comes in. If this is an example of my tree, this could be two different components of it, like omega-1 and omega-2. And each of these maps to a half plane, which these are both the right half plane, but I sort of drawn them together. What can happen is that the one map can send this edge to something that's quite long. And this thing maps it to something which is shorter. But we have to glue these together. Well, how do we glue a long thing to a short thing? Well, the secret is that we can apply quasi-conformal mapping so that if we take this piece here, it maps to something that goes like this. And what you can see is that some of these edges over here are being mapped to a spike that's internal to the half plane. And what's left over is exactly enough segments on the boundary so they match up 1-to-1 with the other side. So even if we had like 10 to the 6th over here and only 10 squared segments over here, we can fold up enough of them so that we have 100 on both sides, and then we can glue. And the difficult part is to do this folding picture, keeping the quasi-constant that you're using uniformly bounded independently of how bad it is. Even if it's 10 to the 10 to the 10 to the 10 to 3, you want to fold up all but 3 of these edges and leave 3 left so that they glue to the other side. And I will not show you how you get rid of the other immense number, but basically on the other side, what you get is some, not quite slip picture, but you get some complicated tree picture over here. But there's 1, 2, 3 things left on the boundary that can be glued to the other side. And creating these trees is where the term folding comes in, that you're folding the half plane into itself so that you can do this. Okay, so the point of the talk, though, was just to state the theorems, not prove them, but to give a few applications. All right, so one where it works out pretty well, this is the simplest one, is suppose that we just want to build a function so that on the real line, it goes to infinity as fast as I want. You give me a function like e to the 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 z squared, and say, I want a function with only 2 critical values that grows faster than that. And the tree you build is this picture. It's basically a union of half plane or half strips. So most of these things look like half strips. But there's one strip here which is getting narrower and narrower, okay? So we're going to talk about that in a second. On these regular strips, we're just taking basically evenly spaced points. And you can check this as bounded geometry because all of these edges are straight lines. They're nice in C2. Where they meet, they form a pretty nice star. There's nothing too bad about that. Where this thing is getting narrower, the dots spacing is about the same as the width. So this distance and the distance across is about the same distance. So that gives you the bounded geometry separation. So this is a bounded geometry graph. What about the tau condition? Well, if you take one of these half strips and map it to a half plane, the picture looks something like this. If you were to pull back evenly spaced points, this is basically, roughly, this is the exponential map, approximately. So evenly spaced points go to something which is basically growing logarithmically here. So the evenly spaced points become much, much denser as you come here. So if you're just taking evenly spaced points over here, what you get over here are things that grow exponentially. So as you move out, the gaps get exponentially large. And so they're bounded below for sure. The shortest one is right here in the middle. And as you move up and down, they get longer and longer. So the tau condition is also okay. So the folding theorem applies to this. And there's a quasi-regular function, which basically looks like the conformal map to a half plane on each of these things. And then across the boundary, somehow the magic of folding lets you interpolate between these. And the point is that when on this one track that narrows here, when you map this to the half plane, what you can think of is that in the half plane, each of these little boxes I've drawn goes to an annulus of a certain conformal modulus. And so basically every time you pass one of these dots, you're going up by a factor of 2 in the image. And so by making the pinching as close as you want, you can make this function grow as fast as you want. And so there's no limit to how quickly you can make it grow by just making this 1, 2 very narrow. But what about when you correct it? When you add in this correction factor, this is only quasi-regular. Well, now you have to use a technical thing that says, oops, I went a little too far. Now you have to say a technical thing that QC mappings are Holder. They all grow like at most a power of Z. And so if we're taking something that's growing as fast as we want and we mollify it by something that grows like a power, the new thing still grows as fast as we wish. We just make the quasi-regular thing grow a little bit faster than we wanted to. And this is perfectly okay. And so this was originally due to Sergei Marenkov by a different proof, but you can get it pretty easily from the folding. Questions on this example? Okay, let me try to spend 10 minutes on each of the next 2 examples. So what I told you so far was what we sort of call like the vanilla folding, or just plain old folding. You're mapping each track of the function to a half plane. If you want to, though, you can map a track to the left half plane instead. So instead of mapping it to the right half plane, you can map it to the left half plane. If you do that and you exponentiate it, well, when you exponentiate the left half plane, what you get is you map to the punctured disk. And so the yellow tracks here are tracks of the function which we instead map to the left half plane. And so as you go out to here, you're actually going to 0, so that you can introduce asymptotic values. And it's not too hard to move that 0 to some other point. If you want to approach the point 1/2, for example, you can approach any point inside the disk that you want. We also can introduce bounded components in which the mapping basically looks like z to the n for some power. So we can break the plane into pieces, map some pieces to the right half plane and exponentiate them, map some pieces to the left half plane and exponentiate them, just introduce high degree critical points at other things. So there's a lot of freedom you have. And then the folding theorem says if these boundary graphs satisfy the bounded geometry condition and the R and L components satisfy the tau condition, the things we talked about before, then you can interpolate. Then you can use folding to take these model functions and get a quasi-regular thing which looks like them away from the boundary, and near the boundary the magic happens and you can glue them together. And most of the applications use this slightly more complicated version of folding. You can even, if you want, instead of putting a z to the n someplace, you can put a 1 over z to the n. So we have this notion of a inverted disk component. So that's also possible. This is something invented by Kirill Zebnik. We're going to talk about that next. So given a singular point, F maps it somewhere. We're doing dynamics, maps it around. And what we'd like to know is what can happen. And in the rational case, what can happen was proven by DeMarco, Koch, and McMullen that, so suppose you're given any set X and any dynamics on it. So you're given any finite set X and any mapping of X to itself. Then there's a rational mapping which mimics this. We don't know that we can get this exactly, but for each of the given points, there's a nearby singular value of the rational function. It has to be a critical value. And the rational map sends this approximating set into itself with approximately the same dynamics. So the precise statement is that you can find a perturbation of the singular orbit, and that the action on the orbit is conjugate, or the action of the rational map on this new set is conjugate to the arbitrary map you were given on the original arbitrary set. So it's interesting to know whether you can take epsilon equal to 0. I don't think that's known whether you can exactly hit the set you want, but you can get within epsilon of it. So for any epsilon that you want. And so this appeared a couple of years ago, and Kirill read this paper and he said, well, that's obviously true for meromorphic functions as well. And so this theorem is written in the paper myself and Kirill, but it really is mostly due to Kirill. He had formulated it and proven it. I just stepped in at the end to grab some credit and to make a few refinements to the proof. But basically it says if you're given any set X, which is discrete, a countable set in the plane, doesn't accumulate anywhere but infinity, and you're given any mapping of X to X, so it can map these things, they can map all to one point, you know, they can do anything you want. Then there's a meromorphic function which does the same thing. For each point here, there's a nearby point associated to it, which is a singular in the singular orbit of the meromorphic function. And then these singular points get mapped to each other in exactly the same way. So the points, so you're given an arbitrary set and an arbitrary map, and you can approximate it by the singular orbit of a meromorphic function so that the actions are conjugate to each other. Okay. And so let me try to explain how folding gives you a picture like this. So these dots are the given set. And I basically want to draw a tube which connects them. So basically I'm drawing a curve which connects these things in some order, doesn't really matter which order, and I'm thickening that curve up a little bit, and then I'm making it a little bit extra thick around each of the disks. And so I build a simply connected region like this. This is simply connected, so it maps to the upper half plane. And the way I've drawn it is I drew it this way so that the hyperbolic geodesic that goes from the origin to infinity almost passes through each of these points, the hyperbolic geodesic. Now, it might miss one, it might just go past one, but basically these points all lie on the hyperbolic geodesic connecting the first point to infinity. So when I map to the upper half plane, they basically lie on a vertical line. Maybe they just lie slightly off it, okay? Now this picture is pretty simple. I just have a bunch of points in the plane, which are more or less vertically stacked. And I want to draw a bounded geometry tree that I can apply folding to. And so I do something like this. And so I just put a disk around each of these. Around each of these, I can make it look like z to the n or z to the minus n. Instead of having the critical values exactly at 0, I can really place it at any point of modulus less than 1. If well, that looks like an 11. It's supposed to look like a modulus of 1. Yeah, let me, sorry. So in certain disks, I can place anything in a 1, whereas if I want a singular value to be outside the disk, then what I do is I put a pole there, and then I perturb the pole so that instead of having the critical point at infinity, it has it outside the disk. And then it's easy to add on extra points to make this into a bounded, oops, I got a screen here I don't want. It's easy to add on points here to make this into a bounded geometry thing. So it's just a matter of drawing the pictures. It looks pretty much like the picture I showed you before. But all these are going to be nice R components, and then these are going to be Ds or inverted Ds. And so we can build a quasi-regular function which does what we want here. And then we take this picture and map it back to the other picture. So all this complicated stuff is going on inside here. And then you draw a picture, then you cut the outside up into pieces, and these are all R components. So this is kind of a pain, and it's very messy, and you can see that it's hard for me to draw this picture. But the point is I'm drawing it. Even if I have to take several pages of a paper to describe it, and I have to show blow-ups, like what does that piece look like especially, I'm not invoking any theorems here. I'm simply drawing pictures of what I want to happen. And then I'm checking that these pictures have the bounded geometry property and the tau property. Those are very easy to check by hand, although a little bit tedious. In any case, I can construct a quasi-regular map which has exactly the behavior you want. That when you have this set X, it exactly has this orbit and it maps it around the way you want. And the point is we haven't made any mistake yet. We haven't had to use epsilon. We haven't had to approximate. This construction lets you build a quasi-regular map, a quasi-meromorphic map, which is exactly does what you want. It uses the the given set. The problem is that to make it holomorphic, you got to correct it by the measurable real mapping theorem. You have this phi here. Phi moves everything a little bit. Even if you take phi almost to be the identity, which you can, it still moves things a little tiny bit. It's not exactly the identity map because G is not exactly holomorphic. And so this breaks everything. So now you had X was mapping, G was mapping X to X, but now F has to be composed with phi. So F is the composition. And so now what F does is it maps this point to X, not this point. So it's not mapping X to itself. It's not preserving the thing. So phi messes us up here. And what Kirill saw was how to fix this using a fixed point theorem. So I'm sorry, I'm trying to advance the page, but it's not advancing. There we go. Okay. So what Kirill did was said, we can actually make G map X to Y. So instead of making X go to X, make X go to something else. Make the set X go to a set Y instead. So we're going to get rid of this. We have enough freedom. We didn't have to make X go to X. We can make X go to Y. So the black points are our X's. Think of Y as being a choice of the target from inside a disk around it. It's the red point here. So we can build a quasi-regular mapping which sends the given black X's to the red Y's. Let me see, red probably shows up here. So we can send the black X's are given to us, the red Y's we choose, and they can wander all around here. So they can fill in the whole disk, but the black point stays in the center. Now, when we fix this, when we quasi-conformally fix this map G, we introduce the phi function. Phi moves some yellow point to X, and the composition then maps the yellow point to the black point. So G maps the black point to a red point, and phi maps a yellow point over to the red point. So phi is taking the yellow point to the red point. So what we want is we want black to black or red. We want the same color going to the same color. So we have a mapping either from X to X or from Y to Y. The only way we can make that happen is if the yellow points are equal to the red. So if this red and yellow point were actually the same point, then we'd have this red point being equal to the yellow point, phi maps it to the black point, and G maps it to the red point. So F would be mapping red to red. F would be mapping the approximating set into itself. So how do you get the yellows to equal the reds? Well, this is a fixed point theorem. We can take phi to be as close to the identity as we want. So that's one of the things that comes out of the folding construction. So as the red function is filling in this whole disk, the yellow points, which are the phi inverses of the black ones, they fill in a smaller region inside the disk. They don't wander very far from the black. So this mapping for each Y we get, for each red point we get a yellow point. The yellow point images are a subset of the disk. So by the Browder fixed point theorem, there's some value in which the red point and the yellow point are the same, which the mapping of the red point to the yellow point has a fixed point, and they're actually equal. And then you can actually do this simultaneously on every disk at once. There's an infinite dimensional version of the fixed point theorem. You can make this all work. And this was Kirill's observation that you can do this. So I think Marty Pete and Shishikura also independently came up with a very similar argument. But it's not something I would have ever thought of. In any case, this is how you make it work. You follow kind of an intricate, bare bones construction of the quasi-regular example with the measurable real mapping theorem and the fixed point theorem. So that's very nice. In the last few minutes, let me just tell you a little bit about triangulations. I'd intended to spend about 10 minutes on this, but I don't think I can do that. We'll have to go a little bit faster.
Technically,
is there a question? Yeah, speak up. I can't quite hear you.
Technically, you are kind of about your time, but you can take a couple more minutes to finish,
all right.
Of course.
Let me just take 5 minutes. And yeah, I put on a timer, so I'd given myself 5 minutes because I'm very generous to myself. So if you have equilateral triangles and you glue them together, you can get a surface, and this surface has a natural conformal structure because the triangles do. And it's a question of which surfaces can be built in this way. And it's a famous result that you can build a surface from equilateral triangles if and only if it has a holomorphic map to the sphere with 3 critical values, which are usually taken to be 0, 1, and infinity. If you have such a mapping, what you can think of is that the boundary, you can think of the real line that has these critical values at 0 and 1 and infinity. It divides it into the upper half plane and lower half plane. These are triangles where one edge is the edge from 0 to 1, and another edge is the edge going out to infinity, and the other edge is from infinity back to 0. And the pullbacks of these are then naturally triangles on the surface, okay? What it turns out is that not every compact surface has such a triangulation. There's only if you're taking a finite number of triangles and gluing them together, maybe this edge then gets identified with this. There's only countably many ways to glue together finitely many triangles, but there's uncountably many different compact Riemann surfaces. So not all of them can be done this way. And it was Belly who characterized when they can be done. So that's why we call this a Belly function, is that a compact surface has such a Belly function, has a triangulation, if and only if it's algebraic. That is, you can write it as the 0 set of a polynomial with algebraic integers as coefficients. This is related to Grothendieck's theory of descendants d'enfant. So for compact surfaces, the answer is sometimes yes and sometimes no. And what Lasse and I were interested in was the non-compact case, like the plane. The plane obviously has a equilateral triangulation. I'm showing you a picture of it. Many of you are familiar with triangulations of the unit disk. This is also an equilateral triangulation. It doesn't look equilateral to our Euclidean eyes, but in terms of the conformal geometry, these are all equilateral triangles. There's a reflection that maps each one to the next one, and that's only possible when you have equilateral triangles. And so the question was, which non-compact surfaces have an equilateral triangulation? And the idea is based on the folding theorem, that if you're given some piecewise smooth Jordan domain like this, and we divide up its boundary in a bounded geometry way, we can apply the folding theorem to create folds in this, so that from this point, if you were to map this to the disk, all these edges would have about equal harmonic measure, conformally. And if you do it quasi-conformally, you can actually make them have equal harmonic measure. Okay? What that means is that the inside of this can be mapped to the outside of the disk with equality, that all these points end up being equally spaced. And then when you apply the Joukowsky map, this maps to the outside of the segment. This is the same kind of picture we saw before. What this means is that each individual line segment here maps to the line segment from 0 to 1. And so if I had 2 pieces that were built this way, this piece maps to the line segment from, say, -1 to 1. And this piece also maps to that segment. And everything is arranged so it's continuous, that we can glue a point here to a point here so they go exactly to the same point here. So pictures like this can be glued together to form a bigger picture. We can glue things together like this. And this is quasi-regular here, and this is quasi-regular here. And when you glue them together, you get a quasi-regular map on the whole thing. This is something you can't do with holomorphic functions, but you can do it with quasi-regular. And so the idea is, take your favorite surface, cut it up into pieces. On each piece, you can do this construction. You build a quasi-regular mapping, which is basically a quasi-regular Belly function. You can do that on the adjacent pieces as well. You can then glue them together. And what you get is a quasi-regular Belly function on each piece. It's a quasi-regular mapping to the sphere that only has critical values at the 3 points. Now you solve the Beltrami equation and you get a holomorphic covering map. The problem is that when you solve the Beltrami equation, it's on a different surface. So you change it. So the whole secret on the non-compact surfaces, I won't go through this in detail, but is that when you change a compact piece of the surface, you can re-embed it into the original surface. So this is the secret. So if this was the entire surface and you solve Beltrami, you would get a different surface. But in a non-compact case, by wiggling the boundary a little bit, the new surface re-embeds in the original one. And now this picture repeats. You can make the QR construction. Oh, that's my time. And this is it. So let me just finish off here. Sorry for misjudging the time. But basically, you sweep the problems off to infinity. You can't do it in the compact case, but in the non-compact case, every non-compact surface has a belly function. This has a couple of nice consequences. The one I really wanted to mention, though, today was that when you have any, say, open set on the sphere, you get a finite type mapping of this region into the sphere, and this gives new examples of dynamical systems of finite type. So I apologize for running over. That's the bad manners on my part, but we'll finish there. And thank you for your patience. Okay.
So thank you, Chris, for your speech. Do you have question in live or online?
I have a couple of questions, but maybe
I'll go with the microphone to the questioner.
Yeah, you can ask, although probably you know the answers. Are these the kinds of questions that you really don't know the answer to already?
Are you able to define any natural Galois action on triangulation in non-compact case?
So I'm sorry, I'm having a little trouble hearing you. Let me turn up my volume to the maximum. Please ask again.
In the non-compact case, are you able to define any natural Galois action on equilateral triangulations? Is it possible? Do they have any arithmetic?
Yeah, I'm not aware of any arithmetic. So as a little background to everyone else, I mentioned very briefly, I meant to spend a little bit more time on this. In the compact case, the surfaces that come from equilateral triangulations are very closely related to algebraic integers and algebraic number theory. And there's a connection with the Galois theory of the number fields. In the non-compact case, we still have these equilateral triangles, but now a compact surface is a countable union of triangles instead of being a finite union of triangles. My expectation is that it would be really neat if there was some kind of, analogous, algebraic theory, some kind of maybe Galois theory for transcendental extensions of the rationals, but I'm not aware of that. I don't know how to make that work. I haven't thought really seriously about it, but it would be perhaps a good idea to be trapped in an elevator for a few hours with an algebraic number theory person, but force them into explaining some of that. So I'm not aware of an analog of that for the non-compact case, but
okay, for compact.
And that's more a case of my own ignorance than it doesn't exist.
Okay, thank you.
I think that's a really fascinating question. So
I think there was a question online. Is that correct? Do I understand correctly?
Yes. I wanted to ask maybe a couple of questions about the post-singular set.
yes.
So one question is whether you really need meromorphic functions in order to get the post-singular set, or is it just a matter, an effect of the
so could we get a little with entire functions as well?
Yeah.
It might be possible, but the proof would have to have some new ideas in it. So I don't think the standard versions of welding would work. Standard versions of quasi-conformal folding would work. The point about quasi-conformal folding is that it basically, the original version was designed to deal with bounded singular sets. So really, we're very good at placing critical values at, say, 0 and 1, or at points that are not too far from 0, 1 by perturbing them. If you had a discrete set which stayed bounded, in other words, it was finite, then you could certainly do it without using any poles. But we could do it with rational functions as well by the theorem we quoted from DeMarco, Koch, and McMullen. If your singular orbit that you're trying to match is unbounded, then the standard folding construction will not work. What you would need to do is to take See, the standard folding construction would basically place the critical values inside these D components, which always map to the unit disk or some fixed multiple of the unit disk. What you would need is a version of the folding where you allow different D components to map to bigger and bigger and bigger and bigger disks. And then when you glue them to the R components, you would have to take that into account. And the boundary of the R components would also have to be growing larger and larger. Logically, I guess that can work, but it would not be the standard thing. You would have to write down a new version. Mm-hmm. Now, Kirill Lazebnik and Jack Burkhardt, two of my students, have basically done this. So they've written down more general folding-like constructions where you glue together annuli, which are getting bigger and bigger and bigger and bigger. And so they have done a folding type construction where the boundaries are going off to infinity. And perhaps you could use that construction to place singular values anywhere in the plane that you wanted. I haven't thought about that, and I haven't asked them about it, but that seems quite plausible. But if you want to make a small perturbation of the vanilla quasi-conformal, it's easier to insert a pole and perturb the pole, and then you hit singular values near the origin with one kind of D component, and you hit singular values near infinity with a second kind, the inverted D component. And then that only requires like a small change to the standard presentation. So that was a technical answer, but you're an expert, so I was addressing you.
Yeah. No,
hopefully I didn't lose the rest of the audience the same way. Okay.
I don't know whether there's time for one second question.
Well, my understanding is that there's a coffee break, so people can go off and get coffee, and we can just chat ourselves if we want to. I think the next talk is at 12:30.
So you mentioned whether you can make the set actually, the set of the posting the set actually equal to the actual set.
Right, instead of just getting the epsilon
so
approximation.
I guess for rational maps, it's clear that you can't because there are only countably many postcritically finite rational maps. But in the transcendental case, I guess there's no reason to expect that you couldn't. So as well, I mean, one might think because you're already using, if one was naive, you're already using a fixed point theorem to hit some kind of values exactly. You might hope that you might actually be able to hit the original values exactly as well. Clearly, that doesn't work. It's an easy way to say why.
No.
Okay.
Well, there might be, but I don't know. I'm almost tempted to ask Kirill to jump in if he's in the audience to address it, since it's, as I said, I already gave him credit for the fixed point theorem, and he's applied the idea to some other applications. He probably is a little more familiar with it. So as I understand it, in this argument, there's no evident way of actually hitting the set you want, only hitting a small perturbation of it. But maybe we're just one clever idea from fixing that. I mean, yeah, maybe if you built like two functions and composed them, you could get the thing to go back to where it was before or something. I don't know. But yeah, that definitely seems like something that's worthwhile. I mean, this is just something which was done in the last couple of years, so it's hasn't really been followed up on yet. And so I think we don't know, not because it's impossible, but just because we haven't tried hard enough yet.
Okay, thank you very much.
So clearly we cannot discuss with the speaker over coffee break. So if there are any other quick questions, maybe we could go over it. There is one more question down there. I'll run to the question.
You're getting more of a workout than I am.
Thank you. Yeah, I was just curious if there was if I just missed it maybe, but was there an upshot to the Bellier triangulations to these meromorphic transcendental functions?
So there are two sort of separate applications. One was to specifying the post-critical orbit. So the hope was that the audience would be interested in the orbit of the singular points and how well you could specify them. And so that was one application. The second application was to the triangulations of surfaces. They're really separate applications, but they both sort of have their foundations on the idea of quasi-conformal folding to build quasi-regular models of what you want, and then you have to take a QC correction map to change the quasi-regular model into a holomorphic model.
Okay.
And in both cases, you have to come up with some kind of argument that the fixing to make it holomorphic doesn't destroy the property you want. But the two applications are separate. Really, probably it would be best to try to give an hour-long talk on each of these applications and explain them fully, as opposed to trying to do a 10-minute summary of each one. That's perhaps a little bit ambitious.
Okay, thank you.
Okay,
You're welcome.
so let's thank our speaker again.
And then,